everyone. Today we are going to study adders. In these adders, we are going to study half adder and full adder. So let us start. First, we'll see what actually adders are. In electronics, an adder is a digital circuit that performs addition of numbers. In modern computer, adder resides in the arithmetic logic unit. Adders are important not only in computer but also in many types of digital systems in which the numeric data are processed. So we are going to study two types of adders, half adder and full adder. So first we'll see half adder. The half adder accepts two binary digits on its input and produces two binary digits output. We have seen in case of gates, logic gates, usually we had two inputs and only one output. But in case of adders, here in half adder, we'll be having two inputs and two output. The two binary digit outputs are, first is the sum bit and another is the carry bit. The half adder is an example of simple functional digital circuit which is built from two logic gates. The half adder adds to one bit binary number. So let us see which gates we had used to form half adder. Here we can see half adder where we have XOR gate and one AND gate. This XOR gate will give you the sum output and this AND gate will give the carry output. This half adder diagram can be simplified by simply connecting OR, AND, NOT and one AND gate. So this is simply nothing but the XOR gate and AND gate, which gives the output as sum and carry. So sum will be given by XOR gate and the carry will be given by AND gate. The same two inputs, you can observe two inputs. This is A, this is B. A is directed to XOR also and A is directed to AND also. So that's why we can say that the same two inputs are directed to two different gates. First is XOR and the another is AND. The input wires to the XOR gate are tied to the input wires of the AND gate. Isn't it? Thus, when voltage is applied to the A input of XOR gate, the A input to the NAND gate receives the same voltage. The sum of the two bit and the carry, sum of the two bit is sum, which is XOR, which will be given by XOR gate, and the carry is given by the AND gate. Okay. Now will see the truth table to understand this half adder. See, when if we'll deal with this x and y is there, if both the inputs are 0, what will happen? Both the inputs when 0, see, x is 0, y is 0, this will be 0, okay, and one of the input is 0 to this sum, then ultimately the sum will be 0. Okay, this is about sum. Then x is 0, y is 0, and will be 0, and its not will be this carry will be 0. So when both the inputs are 0, carry and sum will be 0. Similarly, for every input, we are going to try this. For the another case, when x is equal to 0 and y is equal to 1. See what will happen? X is equal to 0 and y is equal to 1 will gives you OR as 1. Okay, so this input here is 1. Then your y is 1 and x is 0. So AND will be 0, means this carry will be 0. Okay, and this is 0 over here, so its negation will be 1, isn't it? And here it is 1, it was also 1. So when the two inputs of the AND gate is high, the output will be high. Therefore, here we have sum is equal to 1. Similarly, when x is equal to 1 and y is equal to 0, x is 1, y is equal to 0. Here, output of OR will be 1, means the input of this AND is 1. Okay. Then, x is equal to 1 and y is equal to 0, means the output of this AND will be 0. So ultimately the carry will be 0. Then negation of this will be 1. Means here it is 1 and this is also 1. Both the inputs are 1. Means output will be 1. So again for this case also carry is 0 and sum is 1. When both x and y are 1, then what will happen? Both of them are 1. This will be 1. The input here will be 1. Then for carry, the both of them are 1. Okay, so the output of this AND will be 1. So the carry is 1 and negation of this will be 0. So this input is 1 and here it is 0. So the sum is 0. So finally for when both the inputs are 1, carry will be 1 and your sum will be 0. So what actually happens if suppose we have what we have seen in the half adder? If suppose we have such kind of boolean expression where we are going to have one more carry. See here in this we can have 0 plus 0 will be 0, 1 plus 0 is 1, 1 plus 1 is 1. Okay, 0 and carry 1. Okay, so again with this a carry will be formed and we are unable to add this carry. Okay, so that's why what we need to do is we need to have a one more carry bit, additional bit we require. So what we can say, we require one more input. So that is nothing but the carry input, and the inputs will be x, y and carry input, and the output will be sum and carry output. Okay, so for that purpose we see again I'll show you. So 0 0, what will happen? 0. Okay, and then 0 plus 1 1, carry is 0. In the next step, we have 1 plus 1. Okay. And 1 plus 1 is 0, carry 1. Okay. So here we have 3 times 1. Isn't it? Now what will be there? It would be difficult. It would be difficult for us to take 3 inputs, and that's why we require a additional bit. So this is the simple diagram for full adder. Why we require full adder? Because in half adder we cannot add the 3 inputs. In half adder we have only 2 inputs, x and y. But when we need to add one carry, that we cannot add with the half adder. That's why we require a full adder. This is a simple full adder circuit. And this simple full adder is consisting of 2 half adders. This is the simple diagram using OR, and not, as we had seen in half adder. And the 2 half adders are joined with an OR gate. Okay, so this is nothing but a block diagram. Means this is the one. This is one half adder. This is another half adder, and the 2 half adders are connected with the OR gate. Okay, so here we can add 3 inputs. This is X and Y and C. Okay, so let us see how it works. Okay, this is the full adder diagram for by using XOR gate and AND gate. And simply, as we have seen in the earlier case, it is the combination of 2 half adder with joins by using a OR gate. So we are going to see how it actually works. This full adder circuit, we need 2 half adder. The first half adder will be used to add A and B. Okay, so first half adder. Okay, here we have A and B, and it produces a partial sum. The second half adder logic can be used to add Cn, that is carry input, to the sum produced by the first half. Means simply what is happening here, the first half adder is adding 2 input bits, that is A and B, and the another third bit input is given by Cn. Okay, the sum produced by the half adder to get the final output S. If any of the half adder logic produces a carry, there will be an output carry. So that output carry, that is C out, will be an OR function of the half adder. So this is all about full adder, and now we'll see how actually these 3 inputs will generate the output, that is sum output and carry out. The full adder accepts 2 inputs, 2 input bits, that is A and B, and an input carry, that is Cn. And this generates a sum output S and a carry output C out. Okay, so let us see the full adder truth table. Here we have 3 inputs, A, B and C input, and output we have sum and carry output. Okay, this full adder is usually a component in a cascade of adders which adds 8, 16, 32 bit binary numbers. And this values where we had input values, these when we this keep these input values over here, it works as we simply use them in the logic gates. Okay, simply in our logic gate we use, likewise we are going to use it here. So rather than going for this diagram, full adder XOR, if we see our earlier diagram, that is where we had our, what we can say, AND gate, OR gate, and NOT gate in one half adder. So that by using that diagram, we can easily simplify this truth table. What we had? We had OR, AND, NOT, and one AND. So simply this will be a half adder. So in the full adder, one more half adder is added, isn't it? Or even by applying the XOR values, simply A and B we have this A and B to this. B is even input to this. Okay, A is the input to this. So simply by varying the value of A, B and C input, we can simplify this and we can reach up to the output for sum and carry. This is very similar to half adder. Only what we had done, we had cascaded the two half adders. Why we had cascaded these two? Because we need to add one more bit, and that is nothing but the carry input. I stop here.